Hello friends, this video is a part of the tutorial series by ELISA, a non-profit club of Walchand College of Engineering, Sangli. In this tutorial series, we shall be explaining various engineering concepts from the branch of electronics. My name is Pushkar Shirur and I am going to take the topic Smith charts. So in this video tutorial, we shall go through the concept of transmission lines from the course Electromagnetic Engineering. Let us go through the contents. First, the transmission line parameters which govern the working of transmission lines. Second, the need for transmission line charts, the one shown below. And third, how to use a Smith chart, including a few examples. So what is a transmission line? According to Wikipedia, in communications and electronic engineering, a transmission line is a specialized cable or other structure designed to conduct alternating current of radio frequency, that is, currents with a frequency high enough that their wave nature must be taken into account. So, the last part, which tells us that the frequency is high enough, is a very important point. We can depict a transmission line using the black box diagram which is shown here. The input port has been designated as port A and it has some impedance Z0 and the output port B. So it is a 2 input, 2 output system. This image here shows us the variation of the voltages on the transmission line. The black dots which are moving above, close to each other and away from each other, are the electrons, and the arrows depict the amplitude of the voltages and their direction. The main objective of any transmission line is to provide reliable and error-free transmission of power from sender to the receiver. Transmission lines can be considered as two parallel conductors separated by some distance, but not every pair of two conductors can be considered as a transmission line. We will be discussing such long transmission lines and not the small wires that we use to connect instruments or to connect devices on our printed circuit boards. These really long lines. But why use transmission lines when we can go completely wireless? Well, transmission lines on proper usage can give amazing power transmission performance. Besides, it is still a challenge to transmit electricity wirelessly. If by inventing transmission lines, we get reliable transmission of telephone signals that vary around 1 to 20 kilohertz. They work pretty well for low frequency circuits like the latter, but to our ever growing demand for speed, we must increase the frequency. But increasing the frequency would surely give us speed, but an unusual problem occurs. In this video, I won't tell you the concept of transmission lines, but I will tell you the use of transmission line charts. If time permits, I will try to make a video on that too. Now, we will go through the few basic formulae we need to know before we can start. So basically, we need to know the basic transmission line parameters which are necessary to go to a more advanced concept like transmission line charts. So let us take an overview of the basic transmission line equations. The first and most important equation is the telegrapher's equation. It gives us an insight of how voltage and current vary with respect to both time and distance. So, del square V of x upon del x square plus omega square LC V of x is equal to 0. And with respect to current, del square I of x upon del x square plus omega square LC into I of x is equal to 0. The next important equation is the characteristic impedance. If we consider that the transmission line has losses, then we get the following equation for characteristic impedance, which is Z0 is equal to under root R plus j omega L upon G plus j omega C. The next important parameter is the voltage reflection coefficient, which is denoted as rho L. Rho L can be written as the ratio of ZL minus Z0 upon ZL plus Z0, where ZL is the load impedance and Z0 is the characteristic impedance. Next, we have the standing wave ratio, VSWR, voltage standing wave ratio, which is equal to the modulus of maximum voltage which occurs in the waves, standing waves, divided by the modulus of minimum voltage which occurs on the transmission line. And it is easy to derive that it is equal to 1 plus rho upon 1 minus rho, where rho, as we saw above, is the voltage reflection coefficient. Input impedance is the next parameter for a lossless transmission line, is given by Zin is equal to Z0 into ZL plus J tan Z0. Zin of L is equal to Z0 into ZL plus JZ0 tan beta L divided by Z0 plus JZL tan beta L, where beta is equal to 2 pi by lambda is the wave number. So when we solve the telegrapher's equations, the solution of V of x, that is voltage, and I of x, that is current, is as follows. V of x is equal to V plus e raised to minus sigma x plus V minus e raised to sigma x. And the equation for current will be just V of x divided by the characteristic impedance Z0 with a minus sign, because we taking the sign conventions into account. Rho, which is the reflection coefficient, as we saw above, is Z minus Z0 upon Z plus Z0. This equation is extremely important in terms of transmission line charts, because mainly we will play around with reflection coefficient and the impedance, and the equation for impedance with respect to the reflection coefficient will be given as Z load, that is the load impedance, is equal to the load impedance upon Z0 into 1 plus rho upon 1 minus rho. Okay, so now we move to the next part. We will have a little bit of derivation which is required to get an insight of what really a transmission line chart is made of, or how to make it. So the problem faced by us is, consider a transmission line with some infinite length. Our aim terminated by a load impedance ZA with a characteristic impedance Z0. So the aim is to find the input impedance at a distance of minus L from the load impedance. So how will we do this? Actually, you will need a little bit of basics of transmission lines. At a voltage minima, the input impedance seen by the transmission line is real, and its value is equal to characteristic impedance divided by S, where S is the voltage standing wave ratio. So we know that the voltage standing wave ratio is equal to Vmax upon Vmin. So now Zin of L is equal to Z0 into ZL plus JZ0 tan beta L upon Z0 plus JZL tan beta L, where beta is the wave number. We saw this equation previously. Now what we will do is we will take so now let us manipulate this equation so that we will be able to find the input impedance at a distance of minus L from the load impedance. So let us equate this equation, the input impedance, to a value z0 by s. So why are we doing this? Because the input impedance seen by a transmission line at a distance equal to minus L, which corresponds to the first voltage minima, will be Z0 by S. So after equating this equation to Z0 by S and solving it further to get the load impedance, we get the following equation, and it is fairly straightforward. ZL is equal to Z0 into 1 minus JS tan beta D upon S minus J tan beta D. Now instead of L, I have put D here. Now what we will do is we will separate the real parts and the imaginary parts from this equation. The real part will be RL is equal to SZ0 upon S square cos square beta D plus sin square beta D, which corresponds to the resistive part, and XL, which corresponds to the reactance part, is equal to minus Z0 into S square minus 1 sin beta D cos beta D upon S square cos square beta D plus sin square beta D. Okay, so now we go to the transmission line charts. So the equation that we saw previously, which was the real and the imaginary part of the load impedance seen at a voltage minima, we can see that it is not easy to solve it by hand, at least. Now we have modern calculators which can calculate and handle such calculations with ease. But that was not the case back then. So scientists designed a convenient way to give or map a chart or a graph which is able to depict the input impedance at certain distance from the load impedance. Also, the calculations made by calculators do not provide an insight to what is really happening. So the solution to this is the transmission line charts. So let us consider this equation. V is equal to V naught plus e raised to minus j beta z plus V naught minus e raised to j beta z, where z is the distance from the load impedance, beta is the wave number, and V naught plus and V naught minus are the voltage minima and maxima respectively. Sorry, the maxima and minima respectively. Now let us put a condition that we want to find the voltage at a distance of minus L from the load impedance. So substituting the value of z equal to minus L into the equation, we get V naught plus e raised to j beta L plus V naught minus e raised to minus j beta L. And then we represent it in terms of the reflection coefficient rho. Let us take V naught plus e raised to j beta L common. Then what we get is V naught plus e raised to j beta L into 1 plus rho e raised to minus 2j beta L. Similarly, the current will be just the ratio of voltage and impedance. So current at a distance z equal to minus L will be equal to 1 upon z naught, the characteristic impedance, into V naught plus e raised to j beta L minus V naught minus e raised to minus j beta L. And again, taking V naught plus e raised to j beta L common, we get it in terms of the reflection coefficient. So the input impedance will be simply the ratio of voltage and current. And hence, on solving, we get it as 1 plus rho e raised to minus 2j beta L upon 1 minus rho e raised to minus 2j beta L. So now, let us put this equation to use. Normalizing these terms, we will get a very important relation using which we can easily represent transmission line charts. So, in the above equation, let us substitute Z is equal to Zin upon Z naught and rho L is equal to rho into e to the power minus 2j beta L. And in terms of these new symbols, we can represent Z as 1 plus rho L upon 1 minus rho L is equal to R plus Jx since it is complex, and rho L is equal to Z minus 1 upon Z plus 1 is equal to U plus Jv. Even rho L is a complex number. Now moving on, let us map the impedance equation into the reflection coefficient equation. So we will get a relation of how exactly values represented in the impedance domain will show up in the reflection coefficient domain. So mathematically, one can consider either of the equations as a transformation from one complex plane to another, or as a mapping of one complex variable onto another. Like in signals and systems, we have a mapping between Laplace domain to the Z domain, which is the discrete domain. Let us take some typical values and put them into these two equations. So for example, if we take r equal to 1 and x equal to 0, so we get this point here, and correspondingly in the reflection coefficient domain we get u is equal to 0 and v is equal to 0. Then for point B, r equal to infinity and x equal to infinity, it will be some point outside this graph, which will come out as u is equal to 1 and v is equal to 0. So this is point B and this one is point A. Then we have point C, r is equal to 0 and x equal to 0. That is this point. Correspondingly, we get u is equal to -1 and v is equal to 0. So this is point C. Then we have point D, r is equal to 0 and x is equal to 1. So we get this point here in the impedance domain, and correspondingly in the reflection coefficient domain we get u is equal to 0 and v is equal to 1. So u is equal to 0 and v is equal to 1. This is point D. Then we have point E, r is equal to 0 and x is equal to -1. This point here, and mapping that we get u is equal to 0 and v is equal to -1. Hence we can see that no matter which value you take in the impedance domain, you get a value in the reflection coefficient domain which is inside a circle with radius equal to 1, that is a unit circle. So now let us move on. We have these two equations which we have derived earlier, that is z is equal to 1 plus rho l upon 1 minus rho l, where z is equal to z in upon z naught, that is it is the normalized impedance, and z and rho l are both complex. So now let us substitute the values in this relation. We get r plus jx is equal to 1 plus u plus jv upon 1 minus u minus jv. Solving it further, for r and x we get these relations. R is equal to 1 minus u square minus v square upon 1 minus u the whole square plus v square, and x, the reactance part, equal to 2v upon 1 minus u the whole square plus v square. Now if you solve it further, you will observe that you will get the equation of a circle. Similarly, for u and v with respect to x and u and v with respect to r. So now we can see that we get let us again plot these circles taking r and x as some constants. Let us see what kind of a circle that we will be able to plot. So the first equation is this one, and the second equation this one. Now let us put some typical values and observe how they will be plotted in on the graph. So for example, for r equal to 0, we get center 0 comma 0 with a radius of 1. Similarly, for x equal to 0, we get center at 1 comma infinity with a radius infinity. For r equal to half, we get center at 1 by 3 comma 0, radius 2 by 3. For x equal to half, we get a center at 1 by 2, 1 comma 2 and radius 2. Then for r equal to 1, we get center at 1 by 2 comma 0 and radius half, and x equal to 1, we get center at 1 comma 1 and 1 radius. And similarly, you can plot the other two and get the same result. So what can we conclude out of the activity that we did before? Smith chart or a transmission line chart is a plot of constant resistance and constant reactance circles in the reflection coefficient plane. See, for a value of r equal to 0, that is a short circuit across the transmission line, gives us a circle of radius 1, and the reactance circle will have a radius of infinity. So for r equal to 1, we get this circle. And similarly for r equal to 2, r equal to 0.5 and r equal to 0. And for the reactance part, we get for x equal to 0, we have radius equal to infinity. So it will turn out to be a straight line representing the u axis. This is the u axis and this is the v axis. Okay. So now, how do we represent admittance? If one is comfortable with working with admittance, then what should he do? Well, impedance and admittance can be used by the same chart by rotating by 180 degrees from the desired point of interest. So for example, I have the impedance equal to 1 plus j. So here resistance is equal to 1 and the reactance part is also equal to 1. So what I observe here is this circle and its intersection with x equal to 1 circle, and that intersection point will give me the point in the reflection coefficient plane, and if I want the admittance of it, then I will just rotate by 180 degrees. Okay, I will demonstrate it to you again later. Simply remember that use the transformation rho is equal to minus rho if you want to work with impedance. So now let us take a look at this skeleton. It is not the actual Smith chart, but it is a smaller version of it that I have used from the book Engineering Electromagnetics by William H. Height. So here what we have is, we have degrees marked on our circles of resistance, and which is R equal to 0 circle. Hence we have a family of circles: R equal to 0, R equal to 0.5, R equal to 1, R equal to 2, and X. Similarly, for the reactance circles, we have X equal to 2, X equal to 1, X equal to 0.5, and X equal to 0. And similarly for X equal to minus 0.5, X equal to minus 1, X equal to minus 2. Let us consider our previous problem, which was Z is equal to 1 plus J. So for example, you have an impedance of Z is equal to 1 plus J, and you're supposed to plot it on the Smith chart. So how will you do it? Take a point, resistance equal to 1, so it will be this circle. This circle is R equal to 1 circle, and then the reactance part is also equal to 1. So X equal to 1 and R equal to 1. The intersection of those two locus will be this point. And therefore we can easily get other points if we need. So let us move to the numericals. So the aim is to find the reflection coefficient, given that the impedance Z, this is the normalized impedance and not Z in or Z naught. This is not Z in, this is the normalized impedance. So if given the normalized impedance equal to 1 plus J, we have to find the reflection coefficient. So how do we do that? First of all, let us mark the point. The real part is equal to 1 and the imaginary part is equal to 1. So Smith chart is a plot of constant resistance and reactance circles in the rho L plane. So distance from the center will be the magnitude of reflection coefficient, that is the R equal to 1 circle and X equal to 1 circle intersection will give us the reflection coefficient. Because we are in the reflection coefficient plane, the distance, this distance will give us the value of the reflection coefficient, which is approximately equal to 0.45. Okay, and the angle made by this reflection coefficient line will give us the phase. And since we had the equation rho L is equal to rho into e to the power minus 2j beta L, we see that if we increase the distance L, then it only affects the phase of the reflection coefficient and not the amplitude of the reflection coefficient. So I have drawn a circle here with radius equal to the value of reflection coefficient required, and if you move on this constant reflection coefficient circle, then you will get the different phases, and using that you can find the actual reflection coefficient. Phase can be read by the angle made to the u-axis in the counterclockwise direction. That is the convention we use in the complex plane. Let us move on to the next example. Our aim is to find the impedance at different distances from the load. Often we are faced with such a situation to observe how load impedance transfers on a transmission line. Let us consider again the simple example Z is equal to 1 plus J. Z is the normalized impedance. If we get such a problem, we have to move from the load point. This is our load point. We have the relation rho L is equal to V naught minus e raised to minus j beta L upon V naught plus e to the power j beta L. Or look at this equation. So what do we observe? That as we increase the value of L, it only affects the phase and not the magnitude of the reflection coefficient. Hence, if you draw a circle with radius equal to rho L, constant reflection coefficient circle, then we get the path on the transmission line. The second point that we must observe is how much to move. So we now have a constant reflection coefficient circle which tells us the nature of our transmission line. So now we want to find impedance at different distances. So how much do we move from this point? So it is fairly simple. We have this relation, angle is equal to 2 beta lambda, where beta is the wave number and lambda is the wavelength. So for example, if you want to find the impedance at a distance of lambda by 4, so let us substitute the value of lambda by 4 into this equation. So 2 into 2 pi upon lambda into lambda by 4 will give us pi. So if we want to find the impedance at a distance of lambda by 4 from the load, we have to move 180 degrees from this point, which will give us, we have to find the reading at a diametrically opposite point here, or we can even travel from here. So we do not know the direction. So now let us get back to our equation. So what have we observed here? Decrease the value of L, that is, if we move towards the load, then we observe that the angle becomes more positive. Now back to the problem. So how will we move on this circle? We will move either like this or like this. And if we move in the clockwise direction, we are actually decreasing the angle. So we have to move here. Since we are moving away from the load and distance is increasing, hence we have to decrease the angle. So to decrease this angle, we must move this way. And by how much angle? By 180 degree. Then, so moving on to the next commonly faced numerical. Given the load impedance, find VSWR, that is the voltage standing wave ratio. Now, to solve this problem, we must note this very important point. At the voltage maxima, input impedance is completely resistive. Okay? And its value will be equal to S times Z0. So, here we get to know the advantage of a Smith chart. If Z is equal to 1 plus J, again we take this problem for simplicity. Let us mark the point here. So how to find the standing wave ratio without the formula? We know the formula, but we don't want to use the formula because we have the Smith chart. At voltage maxima, input impedance is completely resistive and its value will be equal to S times Z0, where S is the standing wave ratio and Z0 is the characteristic impedance. So, since Z input is equal to S times Z0, so if we take this term here in the LHS, we get Zn upon Z0, which is the normalized impedance, is equal to standing wave ratio. So the normalized impedance is equal to the standing wave ratio. So we move towards the generator. So from the previous example, we saw that if we move in a clockwise fashion, we move towards the generator, that is the origin of the wave. And if we move in the counterclockwise direction, we move towards the load. So we will traverse this circle until we hit the point where the impedance is completely resistive. That is, the reactance part is equal to 0. So if we go towards the generator, we hit this point here. And you simply have to find the value of impedance at this point. So approximately you get this as 2.6, and in a detailed Smith chart using the scale given, you can observe it easily. We can see that this phenomenon repeats itself. So for example, if again you move by a distance of say lambda by 2, or if you move by a distance lambda by 4, you will get a voltage maxima. Shit. So if we move by a distance lambda by 2, so if we move by a distance of lambda by 2 from this point here, we will again get a voltage maxima where the impedance will be completely resistive and its value will be equal to S times Z naught. So let us take a look at the real Smith chart so that it will not be a difficulty when we move to the real one. So this is the actual Smith chart with the actual scale. So the outermost circle is marked in terms of wavelengths. So if I could just zoom, okay. So see the one circle, the circle next to the outermost circle, the penultimate one, we have wavelengths depicted here. So this is 0.01 times the wavelength, 0.02 times, and so on. Then the directions are shown here towards the generator and towards the load. And then in the next circle, we have the markings in degrees and the various resistance circles 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, and so on. And ultimately we reach this point where R is equal to 0. That is the short circuit condition. Similarly, we have the constant reactance circles, these ones. Okay. So now I will quickly show you. So let us take a quick look at software which I found on the internet. It is a Smith chart calculator. So first it asks who are you, the student addition, adds a watermark, and select a student, and then we get a nice little tool which will help us plot the values of impedance, and it has many options: normalized impedance, Z, Y, which is the admittance, move, selected, I don't know these, Z from reflection coefficient, Y from reflection coefficient. So You can use this software if you want to get a feel of the Smith charts and how to plot them. If I miss something from this tutorial, a few references which I used in preparing this tutorial. The first was this website which I found on the internet, and uh, it had a host of it was a host to many softwares which you can use in RF design, electromagnetic engineering related calculations. And finally, the Smith chart calculator, which I found on SourceForge, and this friendly little book, Electro Engineering Electromagnetics by William H. Height and J.A. Buck, and obviously Wikipedia. So, thanks for watching the video. For suggestions, please email us at walchan.elisa@gmail.com. And if you like this video, like us on www.facebook.com/WCESElisa. And that's it for today. Goodbye.